Okay, in chapter 3, section 3.4, there was a special rule that I did not have time to go over in class. It's called Descartes' rule of signs. And so I'm going to go over that briefly in this short video here. There is one question on your chapter 3 quiz in Alex that does ask you about Descartes' rule of signs. Descartes' rule of signs can help us whittle down the list of potential rational zeros that a polynomial function may have, and can in some cases save us a significant amount of time in trying to identify zeros of a polynomial function. So what I'm going to do is I'm going to go to our textbook, and this is on page 336. Suppose that I have a 6-degree polynomial function here. I'm going to apply Descartes' rule of signs to it to show us how the particular theorem works. First of all, we need to warm up to what is considered to be a sign change. Notice that our 6-degree polynomial function that we do not put any placeholders in between our 6th and 4th degree term. All right, as Descartes' rule of signs does not require that we do so. All we do is we count the number of sign changes that occur between the terms of a polynomial. So if I go from a positive to a negative term, that's considered to be a sign change. If I go from a negative to a negative term, that is not considered to be a sign change. I go from a negative to a positive term, that's considered to be a sign change, and a positive to a negative term, that's considered to be a sign change, and a negative to a negative term is not considered to be a sign change. So we can see that in this polynomial here, there are 3 sign changes that occur. So this is Descartes' rule of signs. It is a theorem. It says, suppose that f of x is a polynomial with real coefficients and a non-zero constant term. Then this theorem goes on to guarantee this. Number 1, the number of positive real zeros that the polynomial will have is either the same as the number of sign changes that we experience in f of x, or less than that number of sign changes in f of x by a positive even integer. Furthermore, this theorem goes on to say the number of negative real zeros that this polynomial function will have is equal to the same as the number of sign changes that occur in the function evaluated at negative x, or less than the number of sign changes in f of negative x by a positive even integer. All right, we're going to apply Descartes' rule of signs to help us identify what type of zeros this 5th degree polynomial will have in example 7. So here we have a 5th degree polynomial function here that has 6 terms in it. And notice the coefficients are real number coefficients, and our constant term is non-zero here. Now, to determine the number of potential positive real zeros that f of x will have, we count the number of sign changes that we experience from term to term, left to right. So notice we go from a positive x to the 5th to a negative 6x to the 4th. That is considered to be a sign change. Then I go from a negative 6x to the 4th to a positive 12x cubed. That's considered to be another sign change. Then I go from positive 12x cubed to negative 12x squared. That's another sign change. Negative 12x squared to positive 11x, that's a sign change. And 11x to a negative 6, that's another sign change. So we experience 5 sign changes in this polynomial. Therefore, according to Descartes' rule of signs, the number of possible positive real zeros that this 5th degree polynomial will have is either going to be equal to 5, because there are 5 sign changes, or 5 decreased by 2, which takes us to 3 possible real zeros, or 3 minus 2, which is 1 possible real zero. So this 5th degree polynomial function will have either 5 positive real zeros, or 3, or 1. Now, to determine the number of possible negative real zeros that this polynomial will have, we evaluate the function at negative x. That is to say, I replace x everywhere with negative x, and then I simplify, and then I do another sign count. I count the signs again. So if you take negative x to the 5th power, that's going to be negative x to the 5th minus 6 times negative x to the 4th. Negative x to the 4th is x to the 4th. So this term remains negative. Negative x cubed is negative x cubed times positive 12 turns this into a minus 12x cubed. Negative x squared is a positive x squared times a negative 12 keeps this sign as a negative 12x squared. And negative x times 11 turns this term into a negative 11x, and we got the minus 6. Now we're going to recount our sign changes from left to right. So I go from a negative term to a negative term. That is not a sign change. A negative term to a negative term, still no sign change. Negative term to a negative term, still no sign change. Negative term to negative term, no sign change. And negative term to negative term, no sign change. So there are no sign changes with this fifth degree polynomial when evaluated at negative x. And because of that, ladies and gentlemen, Descartes' rule of signs guarantees that there will be no negative real zeros for this polynomial. It will not have any negative real zeros. Okay, so based on our findings here, what type of zeros would this polynomial be expected to have? To answer that question, we can make a little table here where we have these rows. One row is labeled number of possible positive real zeros, the number of possible negative real zeros, the number of non-real zeros, which are complex zeros that have I in them. And the total of the zeros, including their multiplicities, must always add up to the degree of the polynomial, according to the fundamental theorem of algebra. So one possibility for this fifth degree polynomial is that it could have 5 positive real zeros. And if it has 5 positive real zeros, okay, that means that it would not have any other zeros. We already know that it cannot have any negative real zeros. And if it has 5 positive real zeros, it would not have any complex zeros. So one scenario is that this fifth degree polynomial could have 5 positive real zeros. Or another possibility is it could have 3 positive real zeros, but it still cannot have any negative real zeros, as was determined above by Descartes' rule of signs. But if it has 3 positive real zeros, that means it must have 2 complex zeros. And remember, by the conjugate pair theorem, these complex zeros always come in conjugate pairs. So that makes sense. And that would give us a total of 5 zeros. Another possible scenario is this fifth degree polynomial could have 1 real positive zero, no negative real zeros, but then it would have to have 4 complex zeros. So we would have to have 2 pairs of complex conjugate zeros, and notice we would have a total of 5 zeros. So these are the only possible scenarios that could occur according to Descartes' rule of signs here for this polynomial function. All right. And as it turns out, as I'm after graphing this fifth degree polynomial, you can see the graph here in blue. As it turns out, it does have 3 positive real zeros, namely 1, 2, and 3. And therefore, it would have to have 2 complex conjugate zeros. So as it turns out, the second scenario was the case: 3 positive real zeros and 2 complex conjugate zeros. All right, let's look at example 8 here, which is going to be applying Descartes' rule of signs and helping us to determine the number of possible positive and negative real zeros. Here we have a 6th degree polynomial doing a sign count. And notice you don't have to worry about putting any placeholders in here. Don't do that for Descartes' rule of signs. So we're going to count the sign changes from term to term, left to right. So a positive term to a negative term, that's 1 sign change. Negative to a negative term, no sign change. Negative to a positive term, that's a sign change. And a positive to a positive term, no sign change. Positive to a positive term, no sign change. There were 2 sign changes. Therefore, according to Descartes' rule of signs, we would expect to have either 2 real positive zeros, or 2 minus 2, or 0, or no positive real zeros. Now, when I evaluate this function at negative x, and then re-simplify the polynomial after raising negative x to various powers, I then do a recount of the sign changes. So notice I go from a positive to a negative term, that's 1 sign change. A negative to a positive term, that's another sign change. There's no sign change from a positive to a positive term. Positive to a negative term, that's another sign change. And a negative to a positive term, that's another sign change. So after evaluating, or rather simplifying the function g of x, when I put negative x into it, I count 4 sign changes. Therefore, according to this theorem, this polynomial function is expected to have either 4 negative real zeros, or 4 minus 2, or 2 negative real zeros, or 2 minus 2, or 0, or no real negative zeros. All right, so what are the possibilities? Being a 6th-degree polynomial, if I do have 2 positive real zeros, and let's say maybe I have 4 negative real zeros, well, that would exhaust all the possible zeros this function could have, and therefore there would have to be no complex zeros. Or I could have 2 possible positive real zeros, 2 possible negative real zeros, but then I would have to have 2 complex conjugate zeros for a total of 6 zeros. Or the 6th-degree polynomial function could have 2 positive real zeros, no negative real zeros, but then it would have to have 4 complex zeros, in which case they would come in 2 pairs of conjugates, okay, for a total of 6 zeros. Or I could have no positive real zeros, 4 negative real zeros, 2 complex zeros for a total of 6 zeros. Or I could have no positive zeros, 2 negative real zeros, 4 complex zeros for a total of 6 zeros. Or the only other scenario is I could have no positive real zeros, no negative real zeros, but then I would have to have 6 complex zeros, in which case I would have 3 pairs of complex conjugates for my zeros. Okay, so Descartes' rule of signs here gives us an opportunity to, when we build our list of potential rational zeros using the rational zero theorem, it gives us an idea as to what zeros could maybe be eliminated. In other words, if you cannot have any negative real zeros, you don't even want to try any of the negative real zeros in the list. You just want to try all the positive real zeros. Or if Descartes' rule of signs indicates that you cannot have any positive real zeros, you would just want to try the negative rational zeros in your list. And so Descartes' rule of signs can help us rule out potential zeros for a polynomial and can save us some time. All right, this is good enough for your question on the quiz number 3 regarding Descartes' rule of signs here.